This is now the last section. You should star this section. One question on your final exam will be a question that has to do with this concept. One whole question. This is area under a curve. The first box is the definition that your book gives, which I put in actually the definition from the other textbook I used to use. This one's much easier to follow. Okay, right here. So we are taking the limit as n goes to infinity of a summation of a function. Now a's and b's have to do with where your graph is. So if you look at the picture above, what we're finding is all this shaded stuff underneath the curve. So any kind of fancy curve that we may have between any 2 points, we can use this function to find the area underneath it. You do need to know these. We're going to, if you have functions like this, these are the ones that we need to know. Those are the ones we'll be replacing and stuff. All right, are we ready? So we have this area under the region, y equals x squared from 0 to 8. So if we have this curve, say this is 8 over here, whatever this may be. I would draw a line down here, from here all the way over. That's what I'm finding, all that area. Okay, big long steps though. So now we need a blank canvas to write on. So our function is x squared. A was 0, b was 8. So we start off with area equals the limit as n is going to infinity of the summation of I going to 1 to n of, now I just got to plug a and b in. So it's a plus b minus a, I over n. A is 0, so 0, 0 plus, let me erase this, 0 plus b is 8. 8 minus 0, I over n. Then it's 8 minus 0 over n. So I can simplify this. So this piece here is kind of like a scalar. That's like some number. This is the actual function part. So I'm going to take this 8i over n and plug it into x squared because that's what my function is. So it goes 8i over n squared. Since 8 over n is just a scalar, I'm actually going to factor it out. We can do that. And this becomes 64i squared over n squared. I squared has its own function to change into, and that's what changes to n's. Once you change this to n's, it's a summation of i's, and that function changes. So I leave my 8 over n. I no longer have a summation because I'm actually going to replace this with something else. Here is another scalar. And now I'm going to change my I function, which is from the front page. Now we got to just do lots of fancy math. Well, I can factor out an n here. Six n on the bottom. Oops, n. In parentheses, 2n squared plus 3n plus 1. And then I'm going to factor in 64 and 8. So we get 512n squared, 768n plus 256 all over 6n squared. Oh, I must have reduced something. Oh, I did. These numbers aren't right then. So I reduced the 6 and the 64 on my paper. Sorry about that. So this is 3. Now they're right. And this, remember, we're still taking a limit as n is going to infinity. And they are both n squared, so we get 512 over 3, which is not a perfect number, so just leave it. This section is definitely a section you might want to ask for help on, for sure. I'm going to do one more. I'm going to do 3. Or C. All right, so C, our function is 3x minus x squared. A is 1, B is 2. So the area equals the limit as n goes to infinity of our summation from 1 to n, f of 1 plus 2 minus 1i over n, 2 minus 1 over n. Okay, so now I'm going to take this and put it in my function. I'm actually going to factor this piece out. So 3x, if this is x, this goes there. 2 minus 1 is 1, so this is just I over n minus 1 plus I over n squared. Now keep going with your math. Distribute the 3 in. This squared means there's 2 bubbles. You actually have to FOIL this out. So we get 1. I'll do that on this side so you can see it. So first is 1. Outside, I over n. Inside, I over n. And then backs, I squared over n squared. So this is actually 2i over n. So 1 plus 2i over n plus I squared over n squared. We keep going. So we have 3. I'm going to distribute that negative into each part. So 3 minus 1 is actually 2. 3i over n minus 2i over n is I over n. And then we have minus I squared over n squared. Okay, now here's where we're actually changing the summation numbers to actual n's. So I'm doing the summation of each of these. The summation of a regular value, when you change it to n's, just becomes 2n. So this summation here, just 2n. When I do this one, I'm changing my I term. So I kind of factor out 1 over n, and then I change my I, which is n plus 1 all over 2. And then for this last one, I'm going to kind of factor off 1 over n squared and change that I squared into its formula. n plus 1, 2n plus 1 all over 6. And there's a bracket there. Well, these n's can go away, right? Because there's an n left in this last denominator, I'm not going to cancel the one in the middle. But I do need a denominator for the first term, so I'm going to multiply it by n over n. This becomes 2n squared over n plus. This is 2n, and this becomes n squared plus n. And this one's 6n, and the top is 2n squared plus 3n plus 1. Okay, well, the first term, common denominator would be a 6n, so this one needs a 6 over a 6, and this one needs a 3 over a 3. So our common denominator is 12, oh, not 12, 6, 6n. The first part is 12n squared. The middle fraction is 3n squared plus 3n, and the last fraction stays. Sorry. Now we're going to combine like terms. 12 plus 3 plus 2 is 17n squared. 3 plus 3 is 6n. What did I do wrong? I did something wrong. Did I? Oh, man! It's a minus. Bummer. Minus. Oh, ooh. Minus there, which means that's a minus. That's a minus. This is a minus. Okay, changes these values. This becomes 13n squared. 3n minus 3n goes away, and then we have minus 1 at the end over 6n. That looks better. Okay, with 13n squared minus 1 over 6n squared. Now remember the actual thing says we're taking the limit as n goes to infinity. Leading terms, same exponents, 13.6. Here's a little hint with these questions. If you do these and you don't get leading terms with the same exponents, you did something wrong. All of these questions for area under the curve should have leading terms with the same exponents. So you could just take their coefficients. And that is the end of, whoop, wrong button. Last section.